Alabama STEM Explorers is made possible by the generous support of the HudsonAlpha Institute for Biotechnology, Southern Research, solving the world's hardest problems, the Hawley Family Foundation, Alabama Works, Alabama STEM Council, Alabama Mathematics, Science, Technology, and Engineering Coalition, Alabama Math, Science, and Technology Initiative.
The lamp shocked me. Feels like this always happens. Does this ever happen to you too? I wonder why. I think I know somebody who can help us figure this out. Come on.
Hi, welcome to Alabama STEM Explorers. I'm Sophia, and I'm here with Neil at the HudsonAlpha Institute for Biotechnology in Huntsville, Alabama. I was just telling him about how I keep on getting shocked, and it's really frustrating.
So, Sophia, it sounds like you were a victim of static electricity. So let's talk about what actually might have happened. So tell me, just before you got shocked, what were you doing?
Well, I was really tired, so I walked to the couch, I took off my jacket, I sat down. I may have combed through my hair a little bit, fluffing up this mane. And then I tried to turn on the lamp, and I got shocked.
Okay.
Shockingly enough.
Shockingly enough. So you actually, all those things, you created a whole set of negative charges on your body. And we'll talk about what that actually means, but when you went to go touch the lamp, all those negative charges jumped from your hand to that lamp chain, and that created that spark, that static electricity, that shock. You at home probably have had that same kind of sensation. Maybe you've pulled on or pulled off a sweater, or you've taken a hat off on a cold winter day and then you touch the light switch, or maybe a pet and you got shocked. Static electricity is an imbalance of electrical charges. For example, grab 2 of those balloons. All right, so if we rub the balloon along our clothes, what we're actually doing is we are building up static charge, and if we let go, it should stick. Well, maybe a little bit. It should stick. So the balloon actually sticks to our clothes because of the static electricity. Let's do a different example. Maybe you and I aren't generating much static right now. Let's take a soda can.
Okay.
And you and I each have a plastic PVC pipe. We're gonna charge it. We're gonna add negative charge. You've got that, like you said, that great mane of hair. Charge it by running it along your hair. There's not much mane here at all, so I'm gonna use a scarf. All right, now I'm gonna take this metal can and I'm gonna lay it down.
Okay.
And I'm gonna bring mine really close to it. Now you do yours. You bring yours really close. Pulling it in the other direction. It looks like
tug of war.
Tug of war. Well, come on. Mine. It looks like magic. Sophia, as we talk about static electricity, we need to actually talk about atoms and what atoms are and charges. All physical objects are made of atoms. And I've got a model here, a handmade, homemade model.
DIY.
DIY, that's right. It looks a little bit like some sad kind of Christmas tree ornaments.
I like it.
But each of these are atoms. And you take this atom, and let's talk about what is in this atom, first of all. So all living things, all physical things, not just living things, are made of atoms. This table, Sophia and I, our clothes, the air contains atoms of different components. And atoms have 3 key parts to them: protons, neutrons, and electrons. And we've got them colored in different ways. Here in the center, called the nucleus, are the protons. And we've got the protons in gold, and we also contain the neutrons in brown. They're very tightly clustered together, and the protons and the neutrons are what give this atom its specific identity. Maybe that's carbon, or maybe that's oxygen, or maybe that's lead or gold. It's the number of protons and neutrons in the center of the atom that makes that important. Now let's talk about the electrons around the outside. So they kind of operate in spheres. They move around. They aren't as tightly held as the protons and neutrons. And in this particular one, we've got 5 different electrons. Now, each of these molecules has some sort of charge. Protons have a positive charge. Neutrons are neutral. They don't have a charge. And electrons carry a negative charge. And generally, typically, the proton positive and the electron negative balance each other out. Sophia, let's take a second atom and let's compare. Now, we know that this atom is something different than yours because we can see it has a different number of protons and neutrons in its nucleus. When these two atoms interact with each other, maybe like the way when we rubbed the balloon across our clothing or you rubbed the PVC pipe in your hair, what actually happens is we're transferring electrons. So we're taking the electron off one and we're adding it to the other atom.
But that doesn't change what the atom is.
That's right. Because we transfer electrons, the atom is still the same. That's still, for example, that would still be carbon, and this would still be lead, for example, if that's what it was. The electrons change, but the actual material itself doesn't.
So the only thing different is the charge.
The only thing different is the charge. Okay. So what has happened to the charge on your atom because I took an electron away?
Because electrons are negatively charged, then it's more positive.
That's right. And how about my atom?
It became more negative.
That's right. So we actually now have 2 atoms that have different charges. And when you have a positive and a negative, what happens to them when you bring them together?
They're attracted.
That's right. Opposite charges attract. Now, what happened if I take another atom, and this is the same atom as yours, so hold that one up a second, and I bring it into contact so that I take another one of these electrons away. So now I'm even more negative for this atom, and you've got 2 positives. How do they interact?
They want to stay away from each other.
That's right. Similar charges will repel. So when we look at what's happening with how the balloon sticks, that's because it is opposite charges. But when we look at how things push away, it's because they are similar charges and they're repelling. Let's actually now bend some water.
We can be water benders.
That's right. That's right. This is an activity that's really easy for you to do at home that is a great illustration of how static electricity works. Sophia, go ahead and take your PVC pipe and charge it up. If you don't have PVC pipe at home, you can use a balloon and just rub it against your head or against a scarf. I've got a plastic cup that I've used a nail to poke a small hole in the bottom. So I'll pour water into the cup, and then gravity is pulling the water out of the bottom in a straight stream. But if you bring the pipe near it, do you see how it's bending?
Yes.
Yes, how it's bending. What's actually happening is that negatively charged pipe is pulling the water molecules towards it. Go ahead and try it again. There we go.
Oh,
there we go. See, it's bending it down here. What's actually happening is that water is made up of an oxygen and 2 hydrogen atoms. And together, there's a partial charge that's partially positive down here at the hydrogens, and it's partially negative at the oxygen. So as the water is coming down in a stream, the negatively charged pipe attracts the partially charged hydrogens and it pulls it towards it. But gravity is still carrying most of the work, so it is still falling down instead of running completely sideways. Let's do one more activity that talks about the impact of static electricity. Okay. And that's the levitating orb. And I actually an orb. And you actually have practiced this already. So we've got some Christmas tinsel that we've actually tied into a knot at both ends. So it's 6 pieces of Christmas tinsel. And you're going to charge up the negative, charge up the pole, the PVC pole with negative from your hair. And then we're going to see what happens when we bring the orb, the tinsel orb, near it. Nicely done.
It's floating.
It's floating. So what's happening here is that the negatively charged pole, when the tinsel drops, the tinsel just almost touches, and in some cases touches, and a negative charge is transferred to it. So now we've got negatively charged tinsel and a negatively charged orb. And what happens when we have 2 things with the similar charge?
They want to go away from each
They
other.
want to go away
They
from each
repel.
other, and so they repel. And each of the single strands of the tinsel is also negatively charged, and so they're pulling away from each other as well, which is why you get that beautiful orb. So we've talked a lot about static electricity, and you get shocked because you are generating an imbalance of electrons. You're becoming temporarily negative, and when you touch something, those electrons want to get away from you. You want to go back to your neutral charge. So you can use something that you can spray on, like an anti-static, to help reduce that. Often, static electricity is less in the summer when there's high humidity, when it's not there's not heat and dry air inside. But sometimes we just have to live with static electricity. You're just a charged individual.
I'm a transmission line construction groundsman. When I saw the opportunity, when I saw a flyer, I talked with my family, and I looked at research about it, and I just wanted to be a part of it. Science is always going to be that. You're in the field of electricity, so I feel like that's always going to be something that's going to be used. They do Ohm's law, which is pretty much what, covering a lot about electricity. So a lot of science is going to be used. Technology too, because you're using a lot of equipment. The truck right there, you got tools. When you work in the bucket, you're going to have hand tools. You can have tools that you need to put on lines. So it's always going to be technology as well. I think for me, since I'm a young person, I'll say to people like me who are young, just look at it as a field that it's always going to be there. You're going to always need electricity, and it's almost like we need people for it. And so if you think you can live up to the task of taking that challenge, or doing the science behind it, doing the technology behind all of it, just do it, because you're always going to need electricity. The help is always going to be needed. It's helped me grow as a man, as a person, because you put into, for me, transmission, I'm with different people, and I'm with them almost every day. And so you have to learn on the fly. You got to challenge yourself. You got to, make sure you're teaching yourself, studying, all that. It takes a lot, but I know that anybody can do it. You just got to put your mind and will and put all that into it. Being a part of this now, it's like I don't want to do anything else, I guess. I like it a lot.
I'm Cruz.
And I'm Keisha, and we're here at Southern Research in Birmingham, Alabama.
So what is this thing right here?
This is a Van der Graaf, and we have Molly here with us today, who's going to tell us about the Van der Graaf. But before, I want to give you a fun fact. So this was invented by a physicist named Robert Van der Graaf, who is a native of Alabama in the city of Tuscaloosa. He got his bachelor's degree in mathematics from the University of Alabama, as well as his mechanical engineering degree from the University of Alabama. How awesome is that we're going to look at an invention from somebody who's from our home state? All right, Molly, tell us about the Van der Graaf.
So the Van der Graaf is an electrostatic generator. So how it works is, you can't see it, but there are little brushes both down here and up here, and this belt inside this clear tube moves. So what happens is, as the belt moves, it collects charge from these brushes. And you see this large dome right here. As the belt moves the charges up, they spread out all over the dome, which is what makes the phenomenon happen that we're about to observe with the Van der Graaf. So I'm going to turn it on, and we're gonna see what happens as these charges spread across the sphere.
So when you talk about charges, are you talking about electrons?
Yes. So depending on the Van der Graaf, it could be a positive or a negative charge. It just depends on the particular machine that you're using. But as you can see here, there's lightning, which is super awesome. Yeah. But what is happening is there are so many charges in the sphere that they want to escape. There's so many that they want to get away. And the grounding rod here provides an avenue for them to get back to a less charged area, which is why it's creating this lightning.
Oh,
yeah,
neat.
So there was a lightning last night.
Storm, yeah.
I like that?
Yes. So I remember that lightning too. So it is very similar, yes, because like I was saying, the sphere is just wanting to get rid of charges. It's similar in a cloud. A cloud
that's moving over the Earth is collecting charge as it goes. And so it eventually collects enough charge, just like the sphere, that it wants to get rid of it, which is why it strikes the ground, just like the sphere is striking the grounding rod.
Wow, pretty interesting. I guess you have to be very careful when we're using this Van der Graaf though, right? Practicing safety.
Yes, definitely. As I turn it off, it's pretty easy to get shocked. The shock isn't like dangerous, like you probably you couldn't get electrocuted or anything, but it will give you a pretty nasty shock. I've done it many times. So you can, what I just did there is I grounded it, which means that I can now touch it safely without it shocking me. And because we touched it and the charges went to the grounding rod.
Oh.
So, I have some pretty cool tricks I want to show you guys.
We would love to see them.
Okay. All right. So, you like to blow bubbles, Cruz?
Yeah.
All right. Let's find out what happens when you blow these bubbles at the Van der Graaf.
Okay.
All right. Here, we can use this tool right here. All right. I'm going to remove the grounding rod so we can use the full scale of all of the charges on the Van der Graaf. All right. So I'm going to turn it on, and I want you to blow those bubbles at it.
Okay.
And these are just like regular bubbles that we used when we were playing as a child, right?
Yeah, like I'm sure, like you've played with bubbles before. Like it's just normal bubbles. So go ahead and blow.
Okay,
and
here we
see
go.
what happens.
Oh,
Whoa.
Whoa.
wow. The bubbles are coming back.
Yeah, they're bouncing off.
Why is that, Molly?
So when Cruz blows the bubbles take on the same charge as Cruz, which is a different charge than the sphere of the Van der Graaf. So as the bubbles hit the Van der Graaf, they are immediately taking on the charge of the sphere, which then causes them to repel. So yeah.
Okay.
Because like charges repel other like charges. So
Yeah.
as soon as the bubble takes on the charge of the Van der Graaf, it's going to start to repel the other bubbles. Does that make sense?
Yeah, so that's why they were coming back. Okay.
Yeah.
Yeah, thanks.
Okay, so this is a pretty cool thing that we're able to do with the Van der Graaf too. Have you guys ever seen, like, have you guys ever had your hair stand up or anything like that? Mm-hmm. Yeah, so like that's often a product of static electricity. So here we have this blue wig that we are going to put on our Van der Graaf.
But we're not feeling blue today. We're feeling happy.
Right? No.
Yes.
The Van der Graaf may be feeling a little blue, but we're doing great. All right. So I'm going to turn this on. We're going to see what happens. Whoa!
Oh, whoa. Did you see that, Cruz?
Yeah.
Oh, wow.
So the charges are spreading out throughout this wig because they're wanting to escape the sphere, right? And the wig is sitting on the sphere, so they're wanting to escape. And the hairs are so light that they're just able to lift up. Yeah? So the lighter the hair, the better they lift. You know, Cruz.
He has light colored hair.
Yeah, you have blonde hair. Your hair's looks pretty thin and light. You think you want to try this?
Sure.
It's safe, I promise.
Okay.
I am an expert.
Go Cruz.
Okay, so we're gonna quickly discharge the Van der Graaf. You can see it. So we'll grab that wig off there. Okay, so here Cruz is about to stand on a plastic stool, which is going to make sure that it's basically ensures that all of the charges are gonna get into him and not the ground, if that makes sense. So, Cruz, if you want to go ahead and put your hand on the Van der Graaf, we're going to turn it on and see what happens.
Oh, wow, Cruz. You should see your hair.
Oh, sorry. See?
Wow.
As you can see, there's a pretty you can get a shock if you're not careful. But yeah, shake your head around a little bit. I'm going to turn it up a little more.
Oh, yeah. I can see those hairs standing up.
Look at that go.
Go, Cruz.
That's crazy. So what is happening is the spheres, Cruz, I'm gonna stay away from you. Sorry, I don't want to shock you again. What is happening is the charges are escaping the sphere and they are traveling all throughout Cruz. However, his hair is the lightest part of him, which is why it's standing up like it is. Isn't that so awesome?
That is.
Yeah, I think so too. Yeah. All right, so now we're gonna turn this off. And Cruz, if you want to just go ahead and rub yourself on, just like rub your hands, And what Cruz is doing right now is he is decharging himself, because if he touches anything metal right now, he's gonna get a pretty nasty shock.
And we don't want that.
And we do not want that.
Yeah.
Not gonna lie, that was pretty nerve-wracking.
It was, yeah. I don't blame you. I remember the first 2 times I did it, it was pretty scary for me as well. Okay, so do y'all want to see one more trick? It is my favorite thing that the Van der Graaf can do.
Yes, we definitely.
Okay, it's a real party. I gotta warn you now.
Okay, we're ready for a party. We like parties.
So, I'm gonna quickly tell you all what's gonna happen before it happens. But I'm stacking these pie plates on here. So, the charges in the sphere are going to move up through the pie plates. So, what do y'all think might happen to them?
What do you think, Cruz?
They might fly off.
Yeah,
I don't know.
So.
Let's find out.
Okay, I'm with Cruz.
Yeah.
Let's see. Oh, wow. Let's stand back, Cruz. Oh, look at them go. Oh, wow. Oh, it's a party. Wow.
All right.
That was awesome, Molly.
Wasn't that so much fun?
It
It's
was.
The best.
Party in a pan.
It really is, yes.
Yes. So now that we've learned about this, I think we got a better understanding of why lightning does what it does when we have a lightning storm. So what's going on with that? What are some key things we talked about, Cruz?
Static in your hair.
Yeah, we talked about that.
The energy.
Yeah, the charges.
Charges.
Yes. And remember how Molly said they wanted to release themselves out? And so that is what's going on. So now we got a better understanding, like when we see lightning or even like we run across the floor, you know, you touch a doorknob and get that little shock. Molly, you were an expert. You gave us.
Awesome. Thank
All
you.
right.
That's such a good time.
We had a great time with you today.
So in high school, I was always good with math and science and took several career assessments trying to decide what am I going to go to college for, what's my degree going to be in. All the career assessments pointed towards engineering areas, so I did a lot of research and found engineering has a variety of things to do, and that's what sparked my interest. I have a big passion for helping people, and I saw a lot of engineering disciplines that I could do that and be an engineer. I started my civil engineering with the plans to go into household design, like designing custom homes for people. Once I started going to school, I found my love for what I do now, which is serving people with power. You know, when the lights go out, they need somebody to get the lights back on, and I'm one of those that help make that happen. So we use engineering a lot. Math is a big one. Math, a little bit of science, a lot of design, but I think a lot of our designs come from math bases. So we have a lot of technology features coming into play to help make our systems better. That involves, of course, more math and science and understanding of how systems work. So using our math and science and technology driven, we drive to make things better for us and for people to use. The most rewarding thing to me is when you have a major disaster, like hurricanes that happen all the time. A lot of people lose power. A lot of those lines are down, they're destroyed, and you have to basically rebuild from scratch. After rebuilding those lines and getting power back to the people that have lost it for days or weeks at a time, the joy that's on their face when they see those lights come back on make my job worth it for me.
Thanks for watching Alabama STEM Explorers. If you missed anything or you want to watch something again, you can check out our website at alabamastemexplorers.org. Maybe you have a question we could answer here on the show, and you might grab a cool t-shirt. Feel free to send us a video question or an email on our website, alabamastemexplorers.org. Thanks again for watching. We'll be back next week.
Alabama STEM Explorers is made possible by the generous support of HudsonAlpha Institute for Biotechnology, translating the power of genomics into real-world results. Southern Research, solving the world's hardest problems. The Hawley Family Foundation, established to honor the legacy of Brigadier General Everett Hawley and his parents, Evelyn and Fred Hawley, champions of servant leadership. Alabama Works, a network of interconnected providers connecting business and industry needs to a highly skilled and trained workforce. Alabama STEM Council, dedicated to improving STEM education, career awareness, and workforce development across Alabama. Alabama Mathematics, Science, Technology, and Engineering Coalition for Education, advocating for exceptional STEM education in Alabama. Alabama Math, Science, and Technology Initiative, the Alabama Department of Education's initiative to improve math and science teaching statewide.